Hello and welcome to this video. Today we're going to talk about our EC311 project called Standoff. Our group nickname is Wild West and we're group number 7, and our team members are Nancy, Daniel, Federico, Suyash, and me. Our video is going to be divided into two parts. The first part is going to be the code overview and the test bench to show the simulation and how it works. And then the second part is going to be the demo once we push the code into the FPGA and see how the game works.
Hi guys, so we'll be explaining the PS2 receiver and the keyboard decoder to you. So the input here, we're getting the clock from the FPGA, we're getting the keyboard clock, which is half of the frequency of the FPGA clock, and we're getting 1 bit of keyboard data, and we have to output a 32-bit key code. So here we have an 8-bit current data, 8-bit previous data, and here we're calling the key bouncer so that we can appropriately capture the data coming from the keyboard. We have a key clock coming out of it and the key data coming out of it. Now we move on to this case statement. Here we capture each set of 8 bits coming from the keyboard and put them into current data. Then we go on to putting the current data into our keyboard. Sometimes our important data could be of 16 bits when the key is lifted, and when the key is continuously pressed, our important data is of 8 bits. So we more or less need 32 bits to make up for it, and finally we assign the output to the keyboard out. Now Guillermo will explain the keyboard decoder to you.
So for the keyboard decoder, it's going to take a 32-bit input and then it's going to cut off into a wire to get just the first 8 bits. And that's going to be evaluated in a case statement for different types of keys. So for example, for player 1, the input keys are going to be UIO. And depending on the encoding, it's going to give out different choices for the game. For example, if the key U is being pressed, choice player 1 will have 100 output coming out. And that's going to be the same for different keys. And we also included 3 extra options just in case we might need it. And that's basically the keyboard decoder.
All right, so this is our Livecam module, which takes in 2 inputs and outputs the number of lives, takes in shot and round time, and each player starts with 3 lives, so we initialize num lives to 3. So we have an always block, and at the positive edge of round time, if shot is equal to 0, which means that the player did not lose a life, the number of lives equals the number of lives. Else, if shot equals to 1, which means the player has lost a life, num lives will be decreased by 1. And then over here we have our bullet module, which takes in 2 inputs, the clocks, and 3 bits for the player's action, and outputs the number of the number of bullets. We also have a register, 2 bits for the state, which is initialized to state 1 since the player begins at state 1. And then in this always block, we have a case statement. So the case is for the action. So 001 means duck. So at any state, if you duck, your state will equal to state since you return back to the current state. 01 is reload. So if you're at state 3 and you reload, the max bullet count is 3. So you'll return back to its to state 3 basically. And then else, if you're anywhere else, you will increase, you'll go to the next state. And then 100 means to shoot. So if you're at state 0, you have no bullets left to shoot. So state will equal to state. And then else, if you're any other state, if you shoot, you will go back, you will decrease in state. So you'll go back. And then at the end, we just assign the number of bullets to the state since the output equals the number of bullets.
So going over the computer module, which decides what the player 2 is doing, just takes in the bullet counts and then outputs a choice, also takes in a clock, and the load and reset are for a random number generator. So first, based on the bullet count of the computer, it selects its available options. For example, here 011, that means that you can either reload or duck, but it cannot shoot. Then it filters what a good choice might be. So if player 1 has 0 bullets, it should not duck. So only shooting and reloading is available. And so with those 2 filters, it makes an educated choice. So if available is 011 and good choice is 110, there's only one overlap, there's only one right choice. And likewise for this choice. But then in cases where there are multiple good choices available, then it'll randomly select one of them based on the number outputted by the random number generator. And you can see the case statements here. We flip some of these arbitrarily to make it not duck as often, because I think the random number generator has a certain body. That's it for the computer module.
Okay, so I'm going to go over the outcome calculator, which basically tells the program whether or not the player or the computer got shot. So the inputs are the clock, the choices of the player and of the computer, which in this case is called P2, and the outputs are whether or not the players are shot. So how this works is it evaluates the choices of the two players for every positive edge of the clock. One special case that we should mention is that if both players shoot, then we say that no one gets shot. So nothing happens. You can see if both shoot, the shots are 0. Otherwise, here we evaluate all the other cases. So for instance, if player 1 shoots and player 2 is either in idling or in reloading, he gets shot, and otherwise none of them get shot. And with a similar principle, we have a player 2 shoots. Then I'll briefly go over the audio module. So this works with pulse width modulation. Basically, we only output the sound if the player reaches 0 live. So the way we modulate the output of the audio is with a counter variable that we have here that is increased for every positive edge of the clock. The frequency is determined by the clock divider. And as you can see here, the output of the speaker is turned on only if the lives of the player are 0.
Okay, so this is the test bench for a top module that does not include the keyboard because we weren't able to write a test bench with that in. But anyway, this is the player choice that they input. This is the bullet count. This valid, this V choice, is because we make sure that the choice is valid, meaning that they cannot shoot if they have no bullets and they cannot reload if they have max bullets. And likewise for player 2. Now, player 2, here we show the variables I was talking about in that module, what's available and what would be a good choice, and then the actual choice it makes. And these variables of P1 shot and P2 shot comes out of the outcome calculator based on their decision.
Okay, so I'll briefly go over the simulation to check that the code is behaving correctly. So basically, we update the variables for the computer selection every round time, the pause edge of the round time. So we'll be discussing how this works for every pause edge of the round time. So let's see for this one, for instance. The valid choice of player 1 is to shoot, and the valid choice of player 2 is to duck. So the outcome should be that no one gets shot, and that's correct. And then also the bullet count. So as you can see, 1 shot, so his bullet count went from 1 to 0. P2 didn't shoot, so the bullet count didn't change. So quickly to the next pause edge. Player 1's V choice is to duck. Player's 2 V choice previously was to reload. So player 2 reloaded, so his bullet count went from 1 to 2. Player 1's choice was to duck, so it stayed to 0, and no one gets shot. Now we go over here. Player 1's valid choice is to reload. Player 2's valid choice is to shoot. So player 2 shoots, so you can see the bullet count going from 2 to 1. And player 1 chose to reload, so you can see the bullet count going from 0 to 1. And then you can see that player 1 gets shot. Finally, we can discuss this pause edge. Player 1's valid choice is to shoot. Player 2's valid choice is to also shoot. So what happens in this case is none of them gets shot, but as you can see, both of them lose a bullet.
Alright, so that was the code overview and the test bench. And now we're gonna move on to the demo into the FPGA.
So right now we have our module pushed onto the FPGA. Right now it's paused because the switch is on. We just set it to demo time. I'm just gonna show that so right here, it responds based on the keys to your actions. This is player 1. The 3 right there is for 3 lives, and then player 2, 3 lives. Right now the computer's decided to shoot. So I'm gonna unpause it. Disregard the countdown because it is not actually on sync with ground time. So unpause it. So I lost life because I reloaded. I'm gonna decide to shoot now. Now the computer lost a life. I'm gonna duck. Okay. Now I'm gonna shoot.
Okay, I did see that.
So I beat the computer because the life went to 0. And I just heard the sound because life count went to 0. Unfortunately, you cannot hear that because it's only connected to the audio jack. Bullet count, which is right here. So right now it has a dash because I'm reloading and I already have all 3. So I'm gonna go ahead and shoot. And so my bullet count went down. The computer's decided to reload while I still shoot. So mine went down, his went up. So this is just to prove that it's reacting well, and that's it.
Alright, so that was our project. You were able to see our code working with its test bench and the simulation. You were also able to see the FPGA working once the code was pushed in. And overall, that's what we did in the end of the semester for our project in EC311. I hope you enjoyed the video and thanks for watching.